kind of very related to what your presentation.
Oh, is it?
So
What are
my
you doing?
supervisor, give me this link, so I'll attend your presentation.
Oh, all right.
Yeah.
Okay, good.
Actually, my research topic is about membership inference attacks on recommended systems. And it's a branch of privacy and security attacks about machine learning models or recommendation models.
Right.
Yeah.
Okay. All right.
Yeah,
Very good.
very interested about the federated learning.
Yeah.
I see the introduction of your presentation.
Right. Okay. No, well, I'm really pleased. And if there's anything that to people that I'll put up here, yeah, if you'd like to connect, then I'm sure Conor and Rob would be very interested in talking to you. So yeah,
thank you.
do that. I'd be very interested. And we have a lot of people working on, well, a good group working on sort of in the computer science area. So, you know, within our center. So yeah, so connect.
Okay.
Very good. Yeah, that's good. Yeah. And you? Yeah.
I'm doing my master's.
On what topic?
So, yeah, I'm just doing some serial networks.
Right, okay. Mm.
Essentially very long.
Right, okay, very interesting, very good.
So,
How far through are you? How far through are you?
just about to run.
Right. Mm. Very good. It's nice when you get the literature review done, you know the field, you know where the gap is, and then you can move on to the real work. Yeah, that's good. Yeah, it's one of those things, isn't it? What's the time?
It's 2:02.
2:02. It's good.
Yeah, went to that. That makes including all of them. Yeah. Even that's back about went to MSc. Okay. Yes, it's all like 26th of April, so that's. Yes. Oh, that's that's not a calendar. Yeah, well, the issue with the calendar is the one that can go there and go to my meeting. Yeah, at least on my computer, once I step the calendar, I go to my feet. Oh, so it's very hard to track all the calendar. So thank you very much for joining us. The first school colloquium of 2023. I'm studying for Justin, so any complaints today. Now I just wanted to start with you about your country, then I'll hand over to that's for you as well. So
Oh, okay. That's important. So I acknowledge the traditional custodians of the Macquarie University land, the Watamatagal clan of the Darug Nation, whose cultures and customs have nurtured and continue to nurture this land since the dream time. We pay our respects to the elders past, present, and future. So with that, I'd like to pass to Petra, who will introduce our distinguished speaker.
Okay, so I'm very happy to welcome Kerrie to come and speak to us today. Kerrie's a distinguished professor in statistical science and director of the QUT Centre for Data Science at QUT. Kerrie's a fellow of the Australian Academy of Science, the Academy of Social Sciences in Australia, and the Queensland Academy of Arts and Sciences. In recent years, she has been Deputy Director of the ARC Centre of Excellence in Mathematical and Statistical Frontiers and an ARC Laureate Fellow until 2021. And she's a very active member of various statistical societies. Her research focuses on using and developing new statistical and computational methods that can help solve complex problems in the real world in many areas of application. And she has particular expertise on complex systems modeling, Bayesian statistical modeling, and computational methods. And I'd like to hand it over to Kerrie.
Thanks very much, Petra. Well, hi, everybody. Can you hear me okay? Yeah, okay, good. I'm hoping that the people online can hear me. Just sort of a bit of a strange comment, isn't it? Because if they can't, then they're not going to respond. But if you can't, then please let me know. Right, I want to talk about dealing with sensitive data. And I want to just first start with a little bit of an introduction about our Centre for Data Science. So our Centre for Data Science at QUT was established a few years ago, and we have now it goes across the university. So it's called a Tier 1 centre. And we have people from across the university involved in all things to do with data science. So we have about 140 researchers in the centre. We have about 120 high degree research students involved in the centre. It crosses 5 faculties, and we have about 20 partner organisations, so external organisations that are involved with us. We have 4 core programs. In fact, we have there's one that's been split, and we have 11 foundation applied domains. So we have this sort of core research programs. We have these applied programs, these domains that sit around those, and then we have our partners, and there's a lot of permeability in between. So just to give you a flavour of the kind of core programs and the applied domains, you can see here the kinds of things that we do in the centre that we focus on, and in particular some of the offshoots of that, for example, our Data Science for Social Good program that goes across the different domains and programs as well. So within data science at QUT, then this, as I said, goes across the university. You can see some of the groups that are involved in the centre here. And our centre then is one of a number of nodes, about 30 different research centres that we've brought together in data science across Australia. And so this Australian Data Science Network really has as its aim to bring the different research groups together. That's such a fast-moving area, so many different people that are involved, from mathematical sciences and computer science and information science and e-research and the different domain areas. And there's a lot of challenges, a lot of expertise across Australia, but we're a big country, and so we need to be well connected. So, one group that we don't have is Macquarie. So if there's the centre here in Macquarie that would like to join the network, then please feel free. It's very flat organisation, but the opportunities to connect, share different events that are happening, participate in activities, and in particular, if an external entity wants to connect with the data science community in Australia, not necessarily just with one university, but we can then seek the expertise across the country then through the Australian Data Science Network to work with those organisations. So I'd like to acknowledge my colleagues for this talk. Conor, Hassan and Rob Salomone are the drivers behind the work that I'll be talking about. I have the pleasure of working with them and reporting on this work, but all due respect and acclamation to them for the good work that they've been doing in the areas that I'll talk about. And the application area is with our Australian Cancer Atlas, and we have a large team that's involved in that program. So I'd like to start with telling you about this Australian Cancer Atlas. And what we've done here is develop for the first time an interactive cancer atlas of about 20 different cancers at the SA2 level, so small area level, where people can enter in, go to an area of where they live or where they're interested in, dive into that area and be able to pull up incidence rates and survival rates, relative survival for these different cancers, and to then compare them across different cancers. Now, some of the things that you'll see here are really trying to identify not just the numbers, but looking at what we provide are modeled rates here, and also uncertainty, estimates of uncertainty. Now, we believe that this is important because often we have small numbers for the cancers. We need to be careful of privacy, and we also need to provide some robustness in the estimates that or the figures that we're providing. So the model underpinning this is a Bayesian spatial model. And so we have the data that's been brought together from the different states of Australia, a great feat in and of itself to bring the different cancer data together, and then to be able to model this across the 2,000 odd small area levels in Australia for these different cancers. We're now extending this to a space-time model. But before I talk about that, and I'll just mention it briefly, but some of the insights that the Atlas has been able to show us is, for example, what's the difference in spatial disparities? What difference does it make about where you live in terms of incidence and in particular survival? And what you can see here is for different cancers, you can see the standardized incidence rates here, depending on whether you live in urban areas, regional areas, or remote areas. And you can see that for some of the cancers, it really does matter. The rates are higher in regional and remote areas. And this is exacerbated when we look at survival. So for example, with survival, this is for relative survival for colorectal cancer. And what you can see here is that for people who live in very remote areas, then their relative survival is much worse than people who live in urban areas or indeed in regional areas. Now, this shouldn't happen. And so we need to find out the why of this. But even to understand this then and be able to quantify this means that we can start asking the question, how many lives could we save if we didn't have this kind of spatial disparity? And we start to actually add evidence to these kinds of statements. And that evidence then provided, in this case, a range of media articles and an awareness, public awareness, and then government awareness of this, this differential. And that has led then to a policy change to increase the rebate for people who are living in country areas to be able to access treatment. And so we believe that that's actually wasn't only because of the Atlas, but we will actually say it's in part because of the work that we've done and because we've been able to really underpin this with solid statistical modelling and then be able to provide this kind of evidence on the basis of it. So as I said, the Australian Cancer Atlas now, we're undergoing the revision to add in space-time models and also visualizations into this. And another thing that we're looking at doing is to be able to geotag stories to the Atlas. So we know the what and we know the where, but what we don't know is the why. Why are people making the choices that they are? What are they seeing as their sort of treatment journey in cancer? And so we're allowing then a digital atlas that then people can geotag stories to it, and then we can go into those stories, extract information from that, and then add it to our quantitative data. Now, at the moment, this is about what those stories look like, which are dots on the page, but I'll come back to these dots in a minute. Now, of course, one of the challenges that I just mentioned in this work is that the data are siloed. And this happens very often, that we have data in our case, the cancer data coming from the different states and coming from behind the walls of the cancer councils and the health departments. Now, I don't know what it's like in New South Wales, but I suspect it may be like what it's like in Queensland, which is understandably very difficult to access health data and to be able to then use that to combine with other data to be able to gain additional insights. Now, we have also the issue of governance. So if we do access these data, then how do we do that in a responsible manner that preserves privacy and also then provides some robustness in the estimates that we're providing out of this? So the two approaches that I'd like to talk about is ways that we've been thinking of how to deal with these issues of dealing with sensitive data through federated learning and through the generation of synthetic data. So who in this room has been working with federated learning in any way? And what about the generation of synthetic data? Yeah, and so synthetic data can mean a lot of different things to different people. It can mean there's the simulation of data from a model, from a mathematical model, for example, or a physical model, through to generation of ensembles of data and then drawing from those data sets as well. So I'll come back to what we mean in this work as well, but I'd be very interested to hear after this presentation from people who are working in these areas. So I'd like to start with then the idea of federated learning. And with federated learning, what we see is that we want to try and be able to hear what we've been doing is taking the data from the different data sources and bringing them together and forming the one big database that rules them all. You know, so, but instead of doing that, what if we could leave the data where they are, and then we can actually do the analysis in the cloud? So the data custodians still have access, like still are responsible for their data, and we never ever share that data. In fact, we don't even need to see those data. What we need to do is to be able to access those data and to take from that data any kind of summaries or parts of the model that we would need to be able to combine with the other parts from the other data sources. And that's the idea of federated learning. So if any of you have anything else to do, then you can go now, because that's all I'm going to be talking about for the next little while. So what we're going to do then is looking at how we analyze the data without the data leaving the source. And in fact, without anybody else actually seeing those data. So imagine if we could do this. Queensland Health could keep their data private. New South Wales New South Wales Health could keep their data private, and so on around the country. But we can access those data to form national estimates and gain national insights. So that's the aim of the game. And if we can do this, then we can avoid things like legal, ethical, political, administrative, and computational barriers to combining data from multiple sources. We can increase control around the data. We're not trying, the data custodians are the best people to be looking after their data. And we have the potential to improve data quality and timeliness because of that. And we also then can increase inferential capability from small or dispersed data sets. So there's a lot of advantages in this. And the schematic for how this works is, as you can see here. So we have the local data in the different silos, if you want. And those data then are going to communicate with a central agent in the cloud, a central analysis point in the cloud. And there's going to be the communication back and forward between those local nodes and the global node. And that new global model is going to be formed. So there can be some parameters that are going to be estimated using the global data. And then those global parameters are going to get sent back to the local components, the local nodes, and then updated and sent back again, and so on. And this iterates. So you might see this as just an algorithmic exercise. So what is it that actually interests statisticians or modelers? Obviously, it interests some computer scientists in how to make this efficient. But what I'm interested in is when we're looking at these kinds of models and the kinds of ways that we think about analyzing data, does it change how we intrinsically do our modeling? Does it change how we think about our analysis, as well as the algorithmic part? Is there actually a modeling component to this, a statistical component? And is there a place for mathematical innovation here? So back to the Australian Cancer Atlas, just to show what's sort of being done in this area. We started in this journey with the IKNL, which is the Dutch Cancer Agency, that started to do federated learning a number of years ago, just pre-COVID. And they have a collaboration called with Eurocare and IKNL Netherlands, and have provided some open source software for this Vantage 6. And so what they've done then is looked at collaborations between, for example, the Netherlands and Taiwan, and other collaborations between other countries to be able to gain insights at an international level. Now, this would never be possible if you're going to share the data. Taiwan's not going to give its data to the Netherlands and vice versa. But if we can do this in a federated manner, then this can work. And this group has then demonstrated that this is actually possible. And we're looking to be able to join that collaboration with Australian data as well. So what happens then in this is that we have the different nodes, and the nodes will actually, for a generalized linear model, for example, or a general linear model, the nodes will compute different components of the model. And so, so what they will do then is compute these different components and pass those summaries, those computational outputs, to the central node. And then the central node will pass those back again and then form the parameter values. Now, what this means then is that instead of having the usual way that this would work, which is that all of the data are gathered from the different nodes, so from around Europe, for example, so they would be gathered and then sent to a sort of a central database, and the analysis being done there, and the results, the parameter estimates being formulated there. Instead, what happens is that each area keeps its data, and then the analysis is done in the cloud. And so you can see here that this general linear model, or generalized linear model, depending on the outcome, is actually just working by passing those component summaries back and forward until it iterates to a solution. And the actual outcome of that then provides the estimates. And if you have very good eyesight, or you stare at this for long enough, then you can see that the estimates are comparable here. So the question is there a loss of estimation, or uncertainty in the estimation, or is there a change in efficiency in doing this kind of work? But that's basically the idea of this. And there's a number of different endeavors now to be doing this with different kinds of products as well. So federated learning is really starting to pick up. But what was interesting about this for me is that it's a real example of it in practice. So there's a lot of literature now, but where are the actual examples? And this was one of them. So there are currently some open questions, and this is where we focused our efforts. And so the first question is that the current focus is really mostly on horizontally partitioned data. So there are subsets of the same kind of data in the different places. So if you think of the Cancer Atlas, for example, then you have each state actually having the same sort of data, the same variables, the same responses kind of thing, but they're just sort of subsetted. So if you think about this, it's almost like distributed computing. It's got a lot of parallels with that. Now, the other kind of data that we're interested in is vertically partitioned data. So imagine that the Australian Bureau of Statistics has some covariates, the Queensland Health, the health agencies have other variables, and the Australian Institute for Health and Welfare have other variables, and so on. And we want to access those. So now it's not a matter of combining similar subsets of data. We're actually now combining the different covariates and responses that are held by the different agencies. And that's a different kind of mechanism for doing that. I won't talk so much about that, but it's a more challenging approach here. So the second question then is really about the kind of models that we can look at. So what I've shown now is around general linear models. And what we want to do is think about more structured models. So in statistics, we're looking more at like hierarchical models, highly structured models, latent variable models, space-time models, and so on. And these then have different characteristics and different ways that or different components that we would need to be sharing between the local nodes and the global node. Now, the models that have been looked at the moment, GLMs, Gaussian processes, and neural nets, don't really have this sort of silo-specific variables associated with them. So what we see is really what's shown here. We have might have Bayesian federated learning. We might have just straight federated learning. And Bayesian federated learning, we have distributed MCMC methods, as I discussed, Laplacian approximations for GLMs. And in the sort of regular or non-Bayesian federated learning, we have MLE estimations for GLMs and the training of neural nets as well. So this kind of, this is where the federated learning approaches have really focused. The third open question right now is there's a limited type of models that are possible, but also, so in the second approach, I should say, is that what we want to know about is, can we fit sort of generic structured probabilistic models in this federated setting? So instead of just having, you know, a Z, like the latent variables, Zi here, or the thetas, the parameters that we're interested in, what we want to do is think about a structure for that. So we have some parameters that are affecting our local local latent variables, and then those local latent variables are affecting or generating or responsible for generating the data that we might see. And so we have this sort of structure that we want to learn about. Now, the third question is around how we accommodate different kinds of data, so heterogeneous data. Now, this comes about so that we have different kinds of data that might be held in different silos or different nodes, but also different kinds of silo participation. We don't need to update or have every silo do the same thing. Because some silos might be doing something that means it needs to be repeated more often. Some silos might only need to be contributing at a certain sort of time in the process. So, so that again is something that's around the algorithmic invention, but it's also something that tells us about the modeling that we're doing, and especially if we think about how we can do this in an optimal way. Now, these are still open questions, so that, you know, at the moment there's a lot of hand waving, and anybody who's interested in this space and doing things, and I'd be very happy to connect so that we can learn from others as well. So just to talk about how we're going to frame this, it's in a Bayesian framework. So we have Bayesian inference here. So we have the posterior distribution is what we're interested in. So we're interested in theta, these unknown parameters or missing data or whatever else we're trying to estimate from our model. It might be the model itself. So theta is our unknowns, given our knowns, y, so our data, y. And so we're going to say that that's using Bayes' theorem, we're saying that that's a product then of our likelihood, P of y given theta, and our prior on theta, so P of theta. So we have the numerator there is the product of the likelihood and the prior, and then we normalize it by the integration over theta, so we just have P of y as the normalizing constant. And that normalizing constant then is usually the reason why this is computationally difficult, because now we're integrating over all the values of theta. And so we have MCMC schemes, which often target on a log scale then. We have this on a log scale. So we have the log of our likelihood plus the log of our prior. Okay, so that's what we usually target in our MCMC schemes. So a popular alternative to this is variational inference. So often when these likelihoods are more complex or time consuming for computation, then we look for variational inference. Who here has been working in anything to do with variational inference? Anybody? Yep, okay, good. So we've got some experts. If you saw the hands go up and you want to know about this later, then it's people to ask. So what we want to do then is gives us more, it's more scalable, pure likelihood evaluations that are required. And so if we assume a parametric form of the posterior, then this helps us with distributed algorithms. Okay, so that's why we're going to look at variational approaches. it's easier to deal with a kind of parametric function than empirical draws from a function. So if we, the one slide on variational inference says that what we're going to do is we might have this really unwieldy likelihood and prior combination. Okay, so this is the light green, you know, it's just high dimensional space, and it's like, it's not well formed. But the parameter estimates are usually, look, when we look at the area around the parameter estimates, they're usually, well, much better behaved, okay? And we can often approximate them through, for example, a Gaussian distribution. So around our parameter, the true parameter values, I should say, around those parameter values, then they are actually quite well behaved. And so we can approximate that with some parametric distribution. And that's really the aim of the game. So we're going to choose a parametric approximation that then says, okay, we're going to just deal with this darker green area here. We know that there's an error that we might make between what we're doing in the full distribution and the parametric distribution, but we're prepared to live with that for the, and we can quantify that. There's a whole lot of work that's gone into variational inference. And we usually update the variational parameters via gradient descent. And so in this gradient descent world here, what we want to do then is look at trying to move along the path that's going to get us to the optimum value the fastest way. So we're moving across the gradient here. And so this gradient here is this term here, the gradient of L of lambda here. And that our objective function then is the lower bound of the evidence. And the evidence in this case is going to be this log of P of theta given Y, the difference between that and our variational approximation. So we're going to move along that line. So that's what we do in variational inference. And when we think about conditionally structured variational inference, what we're going to do is to think about our global parameters or our global variables that we want to be able to estimate, Z here, ZG, and we're going to estimate them using data from more than one silo. And then we're also going to be interested in variables that are at the local level. So imagine if I'm interested in the Cancer Atlas again, and I want to know about the effect of rurality or urban, regional, remote differences in survival. And I want to know about that at a global level, at a national level, but I also want to know about it for each of the different states. So I'm going to allow the states to have their own variables or their own parameters. And I'm then going to allow those parameters to be drawn from a global set of global distribution. Okay, so I want to know about the global parameters as well. So that's what I'm going to do here. So when I look at this, then I've got a structured variational approximation. Now this structured variable approximation looks awkward, but what we've got then are the latent terms here for the at the global level. We've got the terms that we want to estimate at the global level. We've got the terms that we want to estimate at the local level here. And we're going to say that that is going to be the variational approximation for the global level here, and then a product of the variational approximations that we've made at the local level given the global values. Okay, so that's the structure that we've got. So you can imagine it's sort of, we've got the data, and then we've got those data partitioned into the different silos, and they have their own sets of parameters. And then those parameters or those variables are sort of gathered together, if you want, or dependent on a global set of parameters. So here's our global parameters here. Here are the local parameters here. And we've got these variational approximation going on at the local level and then also at the global level. So that's the structured approach here. So the choice of this variational approximation can be judicious, and the sets of variational parameters for the local latent variables can incorporate this dependency on the global latent variables. Okay, right. So can we fit generic structured probabilistic models in the federated learning setting? So this is something where, as I said, the focus really has been on just general linear models, generalized linear models, no sort of structure. apart from that kind of structure. But now we want to add a level where we have something going on at the local level that we want to know about, and then something at the global level, and they will be controlled by some parameters theta. Okay, so that's what we want to know about. All right, so that's what we want to know about. And what we're going to do now is introduce this variational approximation to that. So instead of working with the distributions themselves, we're going to say we're working with these convenient distributions or Gaussian distributions, the Qs, and these are going to be formulated by these variational approximations here. Okay, so it's in a variational setting. Right, so that leads us then to structured variational, federated variational inference. Okay, so on a Friday afternoon when you're having some downtime, you can talk about structured federated variational inference and see how many times you can say it. What we want to do then is we've got this setting, we've got the gradient information with respect to our global variables is going to be communicated to the server at each iteration. And then it's going to return the approximations as in the standing setting. So I'm not going to go through this model, but you can see here, here's our Z having some distribution at the global level. And then these local parameters are conditional on the Zs. The local ones are conditional on the global parameters here. And our data are going to be conditional on both the local and the global parameters there. So that's the kind of model structure that we're looking at here. Okay, so this kind of model classes are very common for us, these kind of structures. So we see this in hierarchical models. We see this in mixture models. We see this in topic models. We see it in hierarchical VAEs, variational autoencoders. We see this in many different settings where we want this kind of hierarchical structured approach. Right, so the question is, what we want to try and do is think about how we can do this in a most efficient way. So we're going to take multiple gradient descent steps at each silo without communication and then send the results back to the global stage. So can we get away with doing this? And the answer is yes. So I'm going to just go through this and not worry too much, but if you're interested, then please let me know. Right, so that gets us then to looking at GLMs and structured GLMs. But you might say, well, there's more to life than GLMs. What about neural networks and how does it work with a neural network? So I'm going to talk just briefly about the neural networks. So we've got from GLMs to Bayesian neural networks. And so if we think about a general linear model, we have many inputs here, so many covariates and one response. Okay, that's a typical sort of GLM approach. If we have a single output feed forward neural network, we have our inputs going to a single layer, going to a single output. Okay, so a common feature. So there's different architecture, but similar sort of concept. So now we then have a single output feed forward neural network, which we had a look at, and then we also can go to a deep neural network, which you see here. So if we look at this deep neural network, it has multiple layers. And one of the things that we can think about, and when talking about how models sort of connect with each other, is that one of the other areas that we've been looking at is in transfer learning. So how we can do transferability of models from one setup to another. So for example, this was motivated by a project on the Great Barrier Reef where we have a lot of models. We know a lot about the Great Barrier Reef, but we don't know much about Ningaloo in Western Australia. So can we take the learning that we have from the Great Barrier Reef to Ningaloo, like in terms of the environmental and coral cover and dynamics there. Another area where this sort of transfer learning is really popular is in transport. Can I learn about a highway and the dynamics of traffic on a highway and then move it to another highway, move that model to another highway? What needs to change when I move a model from one place to another? Now, if you take a step to the left, what we're actually asking is, if I've developed something in one node, can I then transfer it to another node, right? Now, in transfer learning, in statistics, we can think about this by adding priors or converting, like we need to modify the parameters in some way. In a neural network setup, what we can do is we can think about having all of the layers in the neural network except the last layer. The last layer might be the local layer. It's telling us about the local conditions, but everything else under that is sort of more generic. Okay, that's more about if I'm moving between the Great Barrier Reef and Ningaloo, it's about how the coral, how the coral responds to environmental factors, how it interacts spatially and so on. All of that may be the same, but it's just then the top layer that might change, like the actual local conditions on the Great Barrier Reef versus Ningaloo. So if we think about this in our setting, or in a transfer learning setting, you basically can take off the top layer of the neural network and then make a new top layer for the for your other area, and then use all of the architecture you've got for that sort of still in that Bayesian network, right? So that's the sort of transfer learning idea. But if we do this in our setting, we can think about the same sort of thing. So what we're going to do is think about having all of the structure in our neural network for the deep component still there, but we'll change the top layer for each of the nodes. Okay, so now we're in the world of federated learning. So the question is, can we allow hierarchical pooling of the layers in a federated learning setting? And what we're going to do then is consider the weight in an arbitrary neural network layer for each of the silos, and we model this weight hierarchically across the silos. Okay, so what this means then is that we have our weights as having something to do with our global parameters here, and sorry, the mu and the sigma here, and something to do with our local parameters here. Okay, so these weights then are going to have at each of the layers, we're going to have our global parameters and then our local parameters. And so this is how we can get around this. Okay, so this allows us to have much more complex models. So I'm going to come back now to the Cancer Atlas, and we've talked about how we might do the kind of federated learning for the incidence and survival estimates through the kind of structured approaches I've talked about. But one of the other approaches that we want to talk about is where we have topic modeling. And so this is for our cancer stories. And so we have here a product of experts. I'm just going to see what I've got here. Yeah, so what I'm going to come back to is the Australian Cancer Atlas stories. And what we want to do now is to be able to analyze those stories using topic modeling, okay? And I'm going to use this federated approach. So each story is going to be sort of have its own privacy, if you like, and it's going to then be, but we're going to analyze the topics across those different stories. So we're going to consider a product of experts latent Dirichlet allocation. So it's just how we actually going to understand the story, or extract from the stories the topics and the themes that we have. And the topic word distributions are going to be our global latent variables that we want to estimate from each of the silos. And each document has its own document topic distribution. And those can be estimated locally to the silo where the data is stored. So you can see what's going to happen here. So we're going to analyze each of the documents locally, and then we're going to combine the results globally. Okay. So if we do this, then what we see is that the documents can be split across a number of silos, and we get what we see is that our approach here, the structured federated variational inference, is equivalent to fitting variational inference on the whole data set here, which is good. We have better topic coherence if the model is fit independently on full data than the 3 subsets. So the coherence suffers a little bit from this kind of federated approach, not too much, but a little bit. And you can see that from the results here. And also we see that we've got 2 types of ways that we did this. So the first one was having 100,000 local descent steps and 1 averaging step. As I said, we don't need to do the iteration each step, versus 1,000 local descent steps and then averaging, and we do that 100 times. So just looking at what was more efficient in time. And both of these schemes give us improved topic coherence. And also we can see that we get the same sort of elbow effect. So the same sort of, response that we would get as if we'd done this as a whole model. So this has got promise in the results. And you can see this is promising, and I'm happy to share very soon. I'll be happy to share the paper where the results are, and also discuss this with you some more. So that's talking now about general linear models. It's talking about structured models. We've talked about the topic models we need for the Cancer Atlas. One thing that we haven't talked about is the spatial model. Now, the spatial models are more difficult because if we have this kind of structure, then each of the silos can be analysed in their own components, and then feed the information back. But if we have some kind of spatial structure here, then we need to be communicating. So at each area, if the result of that area depends on its neighbours, then it's no longer like independent silos. Okay, so we need to take into account that kind of spatial neighborhood, and this kind of spatial neighborhood is like very common in the spatial models. So the question is, how do we do this efficiently? And the answer is we've got some ideas. We're working on them, but we're not quite there yet. But it's an interesting open question. Okay, how am I going for time? Okay, good. All right. I want to just touch on the second topic of dealing with sensitive data, and leave federated learning alone and talk now about synthetic data. So one of the questions that we might ask is, instead of giving us your real data, can you give us some data that look like the data but aren't? Now, there's somebody who's working on GANs, adversarial networks. Yeah, and this is used a lot there. Okay, so what we try to do is create a model that a neural network that's going to be able to generate generate some data from it. We compare the data that we have versus the true data versus our generated data, and see if there's any differences there, and then we can update the first model. So this is adversarial neural network going on. A neural network to create the model, a neural network to tell the difference between the data generated from that model and our real data. If that neural network can find some differences, it passes that back to the first one, improves it, and they keep going until they can't find any differences. So it's like creating the real data, but it's not the real data. And then we can share that. Okay, so there's a lot of advantage in that. Now, so we can we can have all the things that you can see here. So there's lots of opportunities here. Now, the interesting thing is that this has been done with images. It's been done a lot with other kinds of data, but hasn't really been done well with text data and with tabular data, sorry. And so in the tabular data, what we want to do is generate synthetic or proxy data that captures the properties of a tabular data set, typically arising from this observational data, observational study. And so what we want to do then is have this synthetic data via deep generative models, and that's been emerging over the last decade, but it's typically been used for image generation. And there's really no coherent framework on the use of deep generative models for tabular data sets. And so what's interesting here then is the choice of the normalization that we would need to use here. The kinds of different classes of deep generative model that we might need to use, the uncertainty about which properties of that deep generative model gives the most desirable statistical properties for certain variable types, the relationship between the different variable types, privacy, and model evaluation. So all of these are kind of things that we need to think about in this area. So we've got some results here where we've got, let me show you, I'm just going to skip through this. What we're going to do then is want to generate a model. The generating model should be flexible and able to repeat the complex characteristics or replicate the complex characteristics within the observed data set. And we want privacy. That's what we've been working towards. Okay, so what we're going to do is look at deep, probabilistic, generative, privacy preserving methods. And that's what we've been working on. So given the time, I'm just going to leave that there as we've been doing some approaches to this using normalizing flows and other approaches. Very happy to talk to people about this work here. We've also been looking at differential privacy. That can be an approach to allowing this privacy preservation here. I'm happy to talk through that if anybody is interested, but I'll leave it at that. Thank you.
Okay, thank you very much. That was wonderful. Thank you. Questions? Oh, yeah.
Yeah.
Thank you very much. I'm just wondering if you have if you can introduce some sources for the second part of your lecture that was about for generating a new data set that's very close. They have actually preserve all properties of the distribution, and you can keep safe all original data.
Yeah, you would like me to speak a little bit more to that?
Also introduce some resources or
some resources?
Yeah.
Yeah, I'm very happy to do that. And I can point you to the paper. What I can do is to send it through to you. We've just completed, we being a royal we, actually, I have to give Conor the credit for this. So Conor has done this as a review for his PhD. He has a very nice review that he's written into a draft paper. And so what I can do is that'll go up on archive. I'm going to speak for him, but we have been talking about that happening by the end of the month. So Conor, if you're listening, then that's the gauntlet's been laid down now. But no, he's very close to it. But it's a very nice paper for showing the resources there, and also the new work, which is the work we've been doing here.
I actually have a few questions. One is maybe very naive. So a lot of the work, I can imagine that on the sort of private data that has to be done locally, I can imagine you would have to engage with the administrators of that data.
Yes.
Are the agencies actually willing to carry out that kind of intense computation for you?
So what we found is that if we provide because you're providing the code, and you do need to then be communicating carefully with the administrators around this, but so it's a bit of a conversation around like what's the advantage of this, but they're very keen to do this actually. So it's good. They want to see these results, because at the moment it's just such a big barrier. Everybody realizes that this is a really big barrier about sharing data. We need access to data. It's these walls that are up at the moment. All sorts of things. So if you think about for us, the Queensland Council of Social Services, that actually administers a wide range of data on children's, protection of children through to unemployment, through to welfare, this kind of thing. And so it's a wide range of services. At the moment, if a person goes to one service, then they get to see that service gets to see them for that snippet of time. But there is no sharing of the information across the different services. And we know, like you read the news and you know what terrible outcomes can happen from this when there's not that kind of general information that's being shared. Now, of course, that can lead to big concerns. What is actually being shared? What's not being shared? But there is a lot of potential for this kind of work.
That's great. Thank you. More questions? Great, Judith.
So that raises the question for me, and this is also, I'm not coming from a statistics background. What does anonymized data mean? Because a lot of people talk about that. And is it just scraping the names off things, or is it a bit more anonymous?
Yeah, so it's interesting. You can have de-identified data or anonymized data.
Yeah.
So it might take the names off it. But for example, one of the reasons why we need to do the modeling as opposed to just putting up the numbers for the Cancer Atlas, for example. So there's an Atlas of Social Health, which is a fantastic resource that you know, but you need to have, for example, more than 5 or 15, depending on which agencies you're talking to, cases or observations in an area before you would produce the numbers in that area. Now, the reason for that is that even if you don't have the names of somebody there, if you know that there are 2 cases in an area and you know one person, then you know that there's somebody else, and it's pretty, you know, and then you may know their age group or you may know their gender. And so you can pretty easily figure out, or you may be able to figure out who it is. So that's the privacy issue. The other issue is that even if I do have this at the aggregated level and I get another set of data and another set of data, or I cross it through another way and provide the information, can I then undo that, that privacy? So the differential privacy is a way then of saying, you know, I must be able to take an observation out and still have the estimates that I would, well, basically what I'm going to do is to increase the uncertainty of those estimates. So I should be able to move an observation from the lower end of the range to the upper end of the range, and it would still be okay. So if I took anybody out, one observation out, then it's not giving away the information about who that person is that I've taken out, and similarly if I put them in again. So that's the idea of the differential privacy.
Sorry, any more questions? Actually, I have one more.
Yeah.
So you've, on the last slide you talked about the privacy issue. So it doesn't seem like it's the kind of thing that ChatGPT would concern itself with, right?
Yeah. So ChatGPT is made up of you know, all the information that it can gather or that has been fed into it. It's an interesting case as to how private, like what the privacy is around that. I'm sure that if you ask the right questions, then you could find, or ask very detailed, specific questions, then you could get some results. You've got to be pretty careful though, because sometimes it makes stuff up. And so, you know, what's real and what's not. I was actually, one of my students came and said, I didn't realize that you'd authored these papers, and showed me 3 whole new papers that I had never authored before, because ChatGPT added them to my CV, and thought, well, you know, they look perfectly credible for this. So yeah, so I think, you know, it's a good question, and one that we do have to obviously be aware of in terms of like what information we're giving up. It's interesting. One of the things about data literacy is also something that we're very working a lot in, is even amongst very literate people, data literate people, what is the information that we're actually giving up, and what is the information that is being shared about us, and what are we able to then get back out of data that's given to us. And this is really important for communities who, especially for remote communities, for example, where they give up data and then somebody makes decisions about them and tells them about the policies that are going to come down on them, but they have no agency with those data. They don't even have to be remote. They can be any kind of communities. There's no agency about using those data and understanding them ourselves. And I think we all just need to be very data literate. I think it's one of those, the reading, writing, arithmetic and data.
Thank you very much. Any more questions? If not, then I think let's thank Kerrie again.
Okay, right, thank you.
Now, Kerrie's going to be with us for half an hour more, unfortunately, because she has to catch a plane. But if you want to.
Kenny, if you would like to see more about the data, the synthetic generation or privacy, differential privacy, I'm happy to go through that, or we can have a chat. Okay, and I'm happy to share the slides.
Okay, great. Thank you.
Is that okay?
Parallel with meta analysis.
Yeah,
anyway.
they do, absolutely, yeah. Yeah. Is it okay? Sorry?
Yeah,
Oh, good.
absolutely.
Hello. Hello.